Today we will be presenting a case study of Sibanye Stillwater's digital twin journey of their mining operations in Montana. This case study is being presented by Nicole Russell from Sibanye and Saurabh Parakh from Mosultech. Mosultech is a modeling and simulation consulting services firm based out of Washington, D.C. We provide consulting services, training, and develop simulation models and digital twins for businesses from a range of different industries. The industries we support range from mining, transportation, supply chain and logistics, manufacturing, all the way to fast food restaurants. We have done quite a bit of work in the mining industry and are very fortunate to have worked with Sibanye Stillwater. I would like to hand over to Nicole Russell from Sibanye to talk about our project.
Sibanye Stillwater is a South African-based precious metal mining company. They are a leader and primary producer of palladium in the world, and also a primary producer of platinum and a leader in gold production. The Nye mine, also known as the Stillwater mine, is the mine that was the center of this project. It is one of Sibanye's Montana-based platinum group metal mines, or PGMs. The Nye mine, as you can see in the center of the screen, was the center for this project. It spans 2 counties in Montana. The mineralization of the ore body is thin, long, and deep, almost like a vertical wall of ore underground. This is a very quick overview of how the underground mine at Stillwater is organized. This is a cross-section of the Stillwater mine facing north. The mine is almost 4 miles long and 4,500 feet from top to bottom. The mine as a whole is broken into numerical areas, which are the dotted lines that you see here. Each horizontal gray line represents a level, which is also numerically based on the elevation. These levels run parallel to the ore body. Each level will then have multiple headings, which are the break-in points to the ore body. Each heading is also named numerically and in reference to the easting location of the heading, with the shaft that you can see in the middle acting as a 0 point. Within each heading, there can be different accesses into the ore body, which are just branches off of the general heading. Since the ore body is vertical, each heading is mined in floors, with the previous floor being backfilled before mining directly on top or directly below. Rounds are going to be the individual chunks of ore that are taken out through mining. So up here at the top, this is going to be the most broad areas to the most specific rounds. This is a general overview of the process each heading goes through to extract the ore. Rock is mined in rounds, which are 14-foot high by 10-foot wide openings, advanced 9 feet at a time along the ore body. The broken rock removed from the heading enters the Muck haul system en route to the surface and the mill complex. The mill grinds the rock and extracts the ore, which is concentrated and shipped to the metallurgical complex for further refining. Leftover ground rock from the mill is routed into the backfill system. When a heading has had all of the ore removed, it is filled with paste, which is cement mixed with ground rock, sand, which is just ground rock, or CRF, which is unprocessed waste rock mixed with cement. Backfilling these headings allows mining to continue up or down along the vertical ore body. So as we just spoke about on the last slide, the headings are mined in rounds 9 feet at a time. All of the boxes seen here are the steps it takes to complete one round. Those steps will be repeated over and over again until the length of the ore for a given floor is mined. At that point, the post-mining activities are triggered, which includes surveying and prepping the heading for backfill. Backfill will then be delivered to the stope, filling the void that was mined, and the heading will be turned back over to the mining group so that they can continue mining above or below the filled void. This gives you an idea of how interconnected and complex the mining cycle is for each heading. In these pictures, you can see some of the equipment that is used in our operation, including muckers, haul trucks, jack legs, which are used to drill into the rock, underground trains, and side-by-sides, which are used for transport. One of the components that we modeled was the Muck haul system. There are 4 different ways that muck can be transported, which you can see here. We have trucks, passes, which are vertical holes between levels, trains, and skips. All of the vertical shapes on the map are muck passes. The muck will be handed off from one form of transport to another, over and over, until the rock reaches the surface in the mill. This means that the actual route of rock from the heading to the surface changes regularly and can be extremely complex. In addition to the complexity of the muck haul system, the backfill system is also complex. The mill that is in black is going to be the only source of tails for the backfill system. Tails then flow into either the paste plant or one of the 2 red transfer points. These 2 points then service one of the 5 blue sand plants, which each service different areas of the mine. In a nutshell, this means that backfill to any one area is not only dependent on the throughput of the mill, but is also dependent on the demand of all other areas of the mine. The long-term goal of this project was to develop a model of the underground mining operations, surface logistics, and the concentrator operation in sufficient detail into a single intelligent system to predict overall system capabilities. We also wanted to integrate this digital twin with key corporate IT systems for data input and model output such as mine plan, surface plant tailing output, and other systems. In addition, we wanted to provide the ability to manually or automatically run and compare scenarios to different potential risks or surplus and be able to proactively adjust plans to meet my needs. So for our immediate goals and problem statement going into this project, we wanted to understand the interdependencies between mining, backfill, and logistics. We wanted to understand the ability of the backfill plants to keep up with the mining schedule and identify when and where bottlenecks were occurring. We also wanted to estimate the mobile equipment and transport fleet requirements that were needed in order to meet mine plan throughput targets.
So jumping ahead here, what is the solution? Motion Tech proposed the development of a virtual underground mine. It started off with a process to develop a very detailed functional specification of this mining process digital twin. This process aggregated knowledge that was either written down in process flow diagrams or was in the heads of experienced mining engineers across multiple teams. The specification process captured how the process currently works, but also how it should work in the future. A simulation model, which we will demonstrate shortly, was developed iteratively. Each iteration built out one subsystem of the mining complex that could be run independently by itself. And this was handed off to the users while Motion Tech worked on developing the next subsystem. We built this model using the AnyLogic simulation software. This simulation environment allowed us to build a model-based application that can be integrated with other applications or IT systems. It scales really well, from high-level modeling to detailed process models, where we have a lot of objects and a lot of business logic written in Java. Following model development, which we did iteratively and final model validation, we conducted scenario analysis, followed by training, knowledge transfer, and handover. Now let's look at some of the key features of this digital twin. This model can be installed either on a desktop or on a server. For desktop users, the model has an Excel front end where the users can define all their model inputs, run the simulation model, and review the results, all without leaving the friendly Excel environment. We use the AnyLogic fluid library to model the movement of sand and paste throughout the underground mine. Using AnyLogic enabled us to write custom business logic in code and have a really tight control on the model behavior. A challenge we typically face in these projects is preparing model-ready input data. In this case, one of the important and ever-changing inputs was the underground mine plan, which is typically developed in a separate tool like Deswik. This plan tracks every piece of ore body in a very detailed manner. So Motion Tech developed an ETL program, so extract, transform, load, to pull in this information seamlessly into Excel without the user requiring any programming skills. And lastly, we modeled the mobile equipment fleets that were deployed at Sibanye as shared fleets. So any mining block could seize and release them in different areas of the underground mine, providing a lot of flexibility in conducting what-if analysis. A simulation model or a digital twin representation of a business system requires us to abstract away from the real-world system to a degree where it can be represented in code but not lose fidelity or accuracy. Here we list a few abstractions we made to implement the model. The first one was modeling underground production mining resources as teams with capacities as opposed to individual drill, blast, muck, haul resources. Here each block has a number of headings that needs to be mined. Mining of a heading is done in rounds. Some headings have 3 rounds, while others may have 2 rounds. Each block has a fixed number of mining teams assigned. In this example, we have 3 teams for the day shift and 3 for the night shift. Each round takes 11 hours to mine, but a shift is only 8.5 hours long. So the team starts a round during the day, and the night shift team has to finish it at night. The night crew has to start a new heading and cannot work on round 2 of the same heading A due to end of shift blasting restrictions. So this way, the model picks the highest priority heading and assigns it to open resources. Once a heading reaches 11 hours of work, it is ready for backfilling. The mining teams in the model programmatically select the next round and next heading shift after shift to represent this real-world operating process. What is different about this approach to modeling when compared to other mining models is that we are not going down to activities at an individual worker level. The reason for this is lack of good data around productivity. And the root cause is everybody does every job in the underground mine without a task mining system. So there's really no good data on averages. Another key abstraction in the model is to represent the 4 sand plants, the 1 paste plant, and the CRF plant as an interconnected fluid flow system with tanks that represent silos for storing inventory of sand that is ready to be pumped to the headings in specific mining areas. The valves are used to regulate which plant gets tailings from the mill. It's used to implement working hours and controlling the flow to the headings, and it's used to implement failures and maintenance schedules. The flow of tailings into the backfill system is based on mining rates. If the underground miners work faster, it results in more tailings to be generated, and that eventually flows into the backfill system. Any excess tailing that is not used for backfilling headings has to be purged into a tailings pond. So the goal of the backfill analyst is to manage demand for fill, current inventory in silos, and regulate flow to minimize such purges to the tailings pond. The third key abstraction in this model was for underground movement of ore from mining phase to the surface stockpiles as a series of logical handoffs rather than using nodes, links, and pathways. At Stillwater Mine, we have 30 plus unique pathways for ore to take with up to 6 different handoffs, engaging 8 different equipment fleets and 4 rail networks. Because in the underground mining, that pathways keep changing over time, it's difficult to define a fixed pathway of ore and waste from one location to the surface. What we did in this model was instead allow the users to define all potential pathways from an underground area to the surface, all the possible intermediate storage locations or passes, equipment fleet that could be used for these handoffs. This way, the model randomizes the flow of ore through the network of route segments or handoffs, engaging different pieces of equipment along the way. Here, we highlight some of the key objects and agents in the simulation model. They are organized by functional area. Nearly all objects instantiated by the model upon model initialization. The users can design most of the scenarios in the future by changing input data just in Excel. To ensure that the model was usable by the Sibanye team and they had ownership of this tool, most of that worked with Sibanye to design the Excel front end, which includes all the inputs, the output KPIs, and dashboards during the functional specification phase. Here is an example of some of the inputs and outputs generated by the model. Here are some animations, dashboards, and statistics rendered while the model runs. The animation is primarily for validating the model behavior, for modelers or developers to debug their model, And finally, to get stakeholder credibility, so they can observe their system in action and trust that the model is reporting numbers accurately. Now we will demo the simulation model. This is the Excel front end. We can launch the model from Excel, watch the underground mining operations, the headings, the blocks, and within each blocks, monitor the status of and mining rates. We can drill down to individual rounds, look at resource utilizations, look at and here's an example of the process behind the scenes. We can jump from mining operations to look at the progress of rounds and headings across all areas, look at the backfill system, and look at demand and supply of fill, and how sand and paste is flowing through the backfill operations. Monitor the flow rates for the different backfill plants. Identify bottlenecks like cement deliveries and other raw material. In the underground muck haul system, we can look at the different ore passes and the content of ore and waste at different locations in the underground mine. Look at all the different equipment fleet used and look at their utilization and what activity they're performing at any point during a multi-year run. Similarly, we can look at trains that are active and what routes they're traveling on, and picking up ore and dropping them off to specific locations. This is the mill, which is a fairly simplified implementation. And we can fast forward the model all the way to the end so the model can export the results back into Excel and review the statistics and KPIs all within Excel. So the key outcome of this digital twin journey is the development of a better backfill schedule estimation process. The current process is manual and requires getting estimates from mining teams on when they will need backfill delivered to their respective headings. The backfill analyst has to match various demand with current and projected inventory levels in silos to allocate fill. This can be a very iterative and circular process that can be very error-prone. Promising inaccurate dates on when a heading will be filled may result in miners waiting, costing the company money and loss in productivity, and resulting in a blame game. Because the process is cumbersome, it is only done once a week. But mining is a dynamic environment where lots of things are changing continuously, like failures causing a heading to slow down, unexpected downtimes for providing structural reinforcements, and worker unavailability. The model-generated forecast is provided multiple times a week in a few minutes, making it easy to conduct what-if analysis to prioritize headings differently to satisfy miners in all areas.
So some of the value creation that we've seen since integrating this digital twin is that backfill modeling and scheduling now takes about 20 minutes instead of an average of 2 to 3 hours per week. Changes in the schedule are easy to execute through the model. Bottlenecks and sequencing issues are being found months in advance as opposed to only 6 weeks. Long-term models are realistic to run every month and instead of every 3 months. Integration across weekly and monthly planning for the backfill has occurred, making our schedules more consistent across the board. Operations is given real-time data on the effects of schedule changes on the backfill plan. Maintenance time and utilization statistics are incorporated into the schedule, and that gives a more real-world prediction of how we're actually going to operate. Scheduling and planning can be done without an intimate knowledge of the mine system and the backfill system. This is going to lessen training time and eliminate the drops in quality in scheduling and planning that occur because new personnel comes in, and it lowers the learning curve on being able to actually accurately plan and schedule the backfill system. So some of the next step that Stillwater is looking at now that we have this model in place is we want to be able to merge this model's capability with the 3D spatial scheduling software that the production group already uses. We want to be able to take the outputs from both of these software systems and feed them into each other in such a way that they will continually update not only the backfill plan, but also the mining plan. We want to expand the logic used in the 3D spatial scheduling software in order to add more detail and more accuracy to the mining prediction process, now that we can actually integrate the backfill information accurately into that system.